Hello, welcome back to another session on bulk nanostructured materials. In the last session, we have discussed about the mechanical properties of multi-layered nanostructures like their interface area density and hardness. We have also started our discussion on the electrical properties of disordered bulk nanomaterials. As an example, we have talked about gold nanoparticles connected by long organic molecules. From the electrical measurements and the IV characteristics of these gold nanostructures, we have seen that the electrical conductivity of nano gold particles interconnected by organic long chain molecules is much more than gold nanoparticles with no interconnections. From the curves, it was also revealed that gold nanoparticles connected by organic long chain molecules are more conductive than those with no interconnections. Also, as the temperature increases, conductivity increases. The conduction mechanism, as I have mentioned earlier, is quantum mechanical electron tunneling. The quantum mechanical electron tunneling happens from one cluster to the other, the next cluster. In quantum mechanical tunneling, an electron can pass through an energy barrier which is larger than the kinetic energy of that particular electron. Let us think about this a bit further. See the figure. This is a system of two similar metal plates separated by an insulator. For an electron to tunnel from one side of the junction to the other, there must be unoccupied electronic states on the other side. We need to have unoccupied electron energy states on the other side. If electron has to be transferred from one side to the second side, the first side to the second side, you need to have unoccupied electron energy states on the second material. For two similar metals at temperature T equal to 0 Kelvin, the Fermi energies will be at the same level as we know, and there are no free energy states available as shown in the figure B. When a voltage is applied across the junction, the electronic energy of one metal increases with respect to the other. Say this is our first metal, the energy level of this metal increases with respect to the second metal. So, we can say that relatively the second metal will have a lower energy compared with the first one, and this is done by the shifting of the Fermi level relative to each other. The number of electrons that can move across the junction, this is a junction, the number of electrons that can move across the junction from left to right in an energy interval dE. Let the energy interval between the two levels be dE, and the number of electrons that can pass from one level to the other, one material to the other material with an energy interval d is directly proportional to the number of occupied states on the left side and the number of unoccupied states on the right side. So, it is proportional to the number of occupied states in this level and the number of unoccupied states in the right side. And this is given by an equation n equal to n1 of E minus EV, f of E minus EV into n2 of E into 1 minus f of E, where n1 and n2 are the density of states of metal 1 and metal 2 respectively. N1 is the density of state density of states of metal 1, that is this metal, and N2 is the density of state of metal 2, the second metal. And Fe, F of E is the Fermi-Dirac distribution of states over the energy. Now, let us see what is the current across the junction. The current across the junction is also given by another equation. It is given by N equal to K integral N1 of E minus EV, N2 of E, F of E minus EV minus F of E dE. Here K is the probability of tunneling through the barrier. If the density of states is assumed to be a constant over the energy range EV, let us assume that the density of states is constant over the energy range EV, then for small values of voltages and low temperatures, this is to be noted specially, for small values of voltages and low temperature, we can consider the equation for current as I equal to K N1 of EF N2 of EF EV, or we may write the equation as I equal to GV, I equal to GV. In fact, it is written like this GNNV, where the proportionality constant G is nothing but the conductance, and it is given by G equal to K N1 of EF N2 of EF into E. Now, the current is directly proportional to the voltage. So, we can see that I is proportional to V, and the junction behaves as behaves in an ohmic manner. So, that explains the current through the gold clustered nanoparticles connected by organic long chain molecules. Okay. Now, let us see some other properties of the disordered bulk nanostructured materials. We shall start with a property which is very useful in metallurgy. The property is called stability against oxidation. Consider the alloy of iron Fe73 boron 13 silicon 9, Fe73 boron 13 silicon 9. It is an alloy made up of iron, boron and silicon. This has shown a remarkable resistance against oxidation at the temperature range between 200 degrees Celsius to 400 degrees Celsius. And the temperature range 200 degrees Celsius to 400 degrees Celsius. The structure consists of a mixture of 30 nanometer particles of two kinds. The first sort of nanomaterials were FeSi, iron and silicon, and the second type of nano clusters were Fe2b, iron and boron. The oxidation resistance is attributed to two factors. The first one is the large number of interface boundaries. The first one is a large number of interface boundaries. Large number of interface boundaries. We know that when you reduce the size of the particles, automatically the grain boundaries increases, and this is counted as one of the reasons for the oxidation resistance of the material. The second factor which contribute to the oxidation resistance is the faster atomic diffusion at high temperature. The second factor is faster atomic diffusion at high temperatures. Let us see what this means. In the material which we have just conducted, that is Fe73 B13 silicon 9, the silicon atoms segregate to the interface boundaries and afterwards they diffuse to the surface. At first they segregate to the interface boundaries, thereafter they come to the top surface. At the surface, these silicon interact with oxygen in the air and forms a protective layer of silicon dioxide. It forms a layer of silicon dioxide, which means silicon is oxidized. But this silicon dioxide layer prevents further oxidation of the material and protects the material below that from further oxidation, and it shows remarkable resistance towards oxidation. Now, another important property of the disordered bulk nanostructured material is their melting temperature. So, we have seen the first property, the stability against oxidation. Now, we will move on to another property. It is called the melting temperature. The melting temperature. Melting temperature. The grain size of nanoparticles has a great bearing on its melting point. It is found that a material containing 4 nanometer size indium, 4 nanometer size indium has lowered its melting point by 110 degrees Celsius. The melting point has reduced by 110 degrees Celsius for this material. Now, let us think about another important property of bulk nanostructured material. This is called a critical current. This is very important. Critical current represented by IC. Now, what is critical current? The critical current is the maximum current that a superconductor can carry. Beyond this critical current, the material returns to its normal state. It is no longer a superconductor. So, this parameter, this critical current is very, very important in the case of low temperature superconductivity. Let us see a material. In Nb3Sn, niobium tin, this is a superconductor, it is a bulk nanomaterial. It is found that as the grain size decreases, the critical current is found to increase. So, if you make a material with lower grain size of niobium tin, you can increase its critical current, which means you can give more current to the material and keep the superconducting behavior intact. And this has special very big practical applications. Now, another important and interesting feature of disordered nanoparticle clusters is that they affect the optical properties of the material. Till now we have discussed about the mechanical properties and certain other properties. We have not seen anything about the optical parameters of the material. Now, we are going to that realm also. Now, we will start studying about the optical properties of bulk nanostructured materials. Let us consider one example. Metal nanocluster composite glasses. Metal nanocluster composite glasses. This is a bulk nanostructured material which is disordered, and this is one of the oldest applications of nanotechnology. You might have seen the colored stained glass windows in old medieval churches. The glasses are embedded with nano-sized metallic particles, and those metallic particles, those nano-sized metallic particles give the glass that particular color. So, the glasses are embedded with nano-sized metallic particles. The color of the glass changes with the size of the metal and the type of the metal. Glass containing low concentration of metal nanoclusters in dispersed state. These nano sized metallic particles should be in a dispersed state inside the glass. They will have a number of optical properties. The color of the glass depends on the peak wavelength it absorbs. This is a common observation. The color of the glass depends on the peak wavelength it absorbs. The peak wavelength absorbed in turn depends on the type and size of the embedded metal nanoclusters. So, the peak wavelength absorbed depends on the type of the nanoparticle and the size of the nanocluster. So, it depends on the type and the size. Look at the figure. The figure shows the effect of the size of nanoparticles on the optical absorption properties of silicon dioxide glass in the visible spectrum. From the figure, it is clear that as the size of the nanoparticle decreases, the peak wavelength of absorption shifts to the shorter wavelength, which means as the size of the nanoparticle embedded in the glass decreases, it absorbs radiation of higher energy. So, we may write it like this: as the size of the nanocluster decreases, size decreases, what increases? The energy of absorption, or the energy of the wavelength which is absorbed mostly increases, or we call it technically the peak shift towards the shorter wavelengths. The origin of this spectrum we have seen could be explained on the basis of plasma absorption in metal nanoparticles. This could be explained on the basis of plasma absorption in the metal nanoparticles. What is plasma absorption? At very high frequencies, note this point, at very high frequencies, this is not occurring at any frequency, but very high frequencies. At very high frequencies, the conduction electrons in a metal behaves like plasma. So, at very high frequencies, the electrons the conduction electrons in a metal behaves like plasma. And what is plasma? Plasma is a collection of ions. And in this particular type of plasma, we know that a conductor is electrically neutral. So, it behaves like an electrically neutral ionized gas. It behaves like an electrically neutral ion plasma. And how is the neutrality established? We need to have negative charges and an equal number of positive charges. The negative charges are the mobile electrons and the positive charges reside on the background atoms. So, you have negative charge in plasma, which are electrons, and the positive charges reside in the background atoms. If the wavelength of the light is greater than the size of the clusters, which are well dispersed in the medium, then the electromagnetic wave causes oscillation of electron plasma. This is plasma absorption, and this process absorbs light. Once again, if the wavelength of the light which is coming in is greater than the size of the clusters, and this is the condition, am I right? If the wavelength of the light that is coming in is greater than the size of the metal cluster, then the electromagnetic wave, that is the light which is coming in, causes oscillation of the electron plasma. This results in oscillation of the electron plasma, and these oscillations absorb light, and this is the reason why plasma oscillation happens in the metal nanocluster glass, embedded glasses. The absorption coefficient of the material for different wavelength can be expressed by a theory developed by Mile. The absorption coefficient alpha, the absorption coefficient is given by alpha. It could be explained by a theory developed by Mile, and it is given by alpha equal to 18 pi ns v n0 epsilon 2 cube by lambda whole divided by epsilon 1 plus 2 n0 square the whole square plus epsilon 2 square, where ns is the number of spheres in volume V. Epsilon 1 and epsilon 2 are the real and imaginary parts of the dielectric constant of the spheres, and n0 is the refractive index of the insulating glass. The metal nanocluster composite glasses exhibit nonlinear optical effects also. They exhibit another property, another optical property to be precise, and the optical property is called nonlinear optical effect. What is nonlinear optical effect? The nonlinear optical effect means the refractive index of the material changes with the intensity of the incident light. The refractive index, let us represent it by n. It changes with intensity of light. That is, normally the intensity has nothing to do with the refractive index of a material, but in the nonlinear optical region for a material which exhibit nonlinear optical effect, the refractive index of the material will change with the change in intensity of the incoming light. The reason for this phenomenon is that the glasses possess an enhanced third order susceptibility. They possess an enhanced third order susceptibility, which causes the intensity dependence of the refractive index, and this is given by the relation n equal to n0 plus n2i. The nonlinear optical effects are used in optical switches, which would be the major components of photon based computers, and this has future applications, potential future applications, as these nonlinear optical effects instruments will be used in photon based computers. So, in this session we have discussed about some properties of the disordered bulk nanostructures. Then we have seen some optical properties like the coloration of glasses, and then the nonlinear optical effects. Thank you.